Bismillahirrahmanirrahim. Sallallahu alayhi wa alihi wasallam. Allahumma rabbi zidni ilma. Sallallahu alayhi wa alihi wasallam. Ameen. Alhamdulillahi rabbil alameen. In this lecture, I will discuss the important concepts of pulleys and important advice. Be of benefit to others. Normal contact force and tension in inextensible string. Tension is the reaction force in inextensible string which is produced when the particle is hung or suspended freely in the air. This reaction force in this string is known as tension because particle is hung freely in the air. And this reaction force is the normal contact force because particle is in contact with the ground and it's equal to weight. And here tension is equal to weight of the particle. In inextensible string, three quantities remain unchanged. Number one, tension. Number two, acceleration. And number three, speed. Tension always acts away from the point of resolving. This concept is very important while resolving forces. Given that following system is in equilibrium, find tension in this string and reaction on object P. Well, tension is because of the hanging particle's weight. So tension in this string must be weight of particle A, which is 40 newtons. In one string, tension remains unchanged. Therefore, tension in this part of the string is also 40 newtons. Since B is in contact with the ground, therefore there are three forces which are acting on B. Number one, weight of B, which is acting vertically downwards because weight always acts vertically downwards. Normal reaction on B and tension. Since system is in equilibrium, therefore all must be balanced. So T plus R is equal to weight of object P. Therefore R is 10 newtons because T is 40 newtons. Free fall or motion under gravity. We always replace A by G in free fall and we take G negative 10 when particle is moving in vertically upward direction and we take G plus 10 when particle moves vertically downward. Equations of motion. You all know this is the first equation of motion, V plus U upon 2. This is the average velocity. If velocity is constant, then we can use this equation in this way. S is equal to Vt or Ut. Now we need to replace A by G in all these equations. So V is equal to U plus Gt, half Gt square minus half Gt square and 2Gs V square minus U square. Make sure you must remember all these equations. At maximum height, you all know velocity is 0 and at same height, velocity remains the same. Important cases. Number one, given that this system is in equilibrium and B is heavier than A and the particles are initially at rest. Well, when you release the system from rest, then B will move in downward direction, or you can say B moves vertically downwards whereas A moves vertically upwards. Since B is moving in downward direction, therefore weight of B is greater than tension. And since A is moving in upward direction, therefore tension is greater than weight of A. And when you will simplify these inequalities according to Newton's second law, you will get these two equations. T minus WA is equal to mass of A times acceleration, and WB minus T is equal to mass of B times acceleration. When B hits the ground, we assume that it hits the ground with speed 3 meters per second and in 2 seconds. And this velocity, this speed, this is the same speed of this particle A at this point. When B hits the ground, the speed of A must be same, like 3 meters per second, because in one string speed remains same, and A must be of 2h height from the ground. Since the speed of A is not 0, it's 3 meter per second, therefore A will move under gravity and the string will become slack. This is the situation. At this point, A is on height 2h from ground and the speed of A is 3 meter per second, which is the striking speed of particle B with the ground, and A will reach its maximum height in t up seconds, and G is minus 10 because this motion is vertically upward. So we have three important informations. We have initial speed of A at this point, we have final speed of A, we have G. So with the help of these three informations, we can get time taken by particle A to reach its maximum height when B hits the ground, and that time is denoted by T slack up, and we can use this equation for that. V is equal to U plus GT, and we assume that this time is 0.5 seconds. A will come back from after reaching its maximum height, it will come back to its height 2h, and the string will become taut again, and this total time will be twice of T slack up, because in vertical motion time of flight will remain same. So if this time is 0.5 seconds, then this time will also be 0.5 seconds, meaning time that elapses until this string becomes taut again is twice of this time, or you can say 2T slack up. Similarly, we can get the S up distance with the help of this equation, 2gs v square minus u square, and this distance means distance traveled by the particle A to reach its maximum height when B hits the ground. And if this distance is 1 meter, let's suppose, then this distance will also be 1 meter. So we can also get the total distance. Total distance is twice of S slack up, and you can read this as total distance traveled by A when B hits the ground until the string becomes taut again. And this is the velocity time sketch of the motion of both the particles. This is the sketch of particle B. Particle B starts from rest and it hits the ground with the speed velocity 3 meter per second in 2 seconds, and it will remain at rest for the further 1 second, because this time is 0.5 seconds T slack up, and this total time is 1 second. So B will remain at rest for 1 second. Make sure you must mention this thing. This means B remains at rest for the further 1 second. Well, this is the graph of particle A. Particle A starts from rest, it hits the ground, it reaches the height of 2h meters from ground in 2 seconds. And then this is the motion under gravity. This is the motion when particle reaches its maximum height in 0.5 seconds. And then this is the motion when particle come back to its height 2h from ground and string becomes taut again, and the time is same 0.5 seconds. Make sure you must label the axis. This is time in seconds, velocity in meter per second, and this is the key. This is for A and this is for B. Case 2. The system is in equilibrium and particles are at rest, and given that B is heavier than A. When the system is released from rest, then particle B is moving vertically downward and A is moving towards the pulley. Since particle is moving vertically downwards, therefore weight of P is greater than tension, which is here. And since particle A is moving towards the pulley, therefore tension is greater than friction. And normal reaction is equal to weight of A. So we have three equations. Well, when B hits the ground, then A will be here. Let's suppose A is here. And B hits the ground with speed VB, then this would be the same speed of particle A at this point, because in one string speed remains same. Since the speed of A is not 0, therefore A will move towards the pulley and will continue to move towards the pulley in fact, and string becomes slack. And it's given since A does not reach the pulley, therefore A will come to rest before the pulley, and therefore its final speed is 0, its initial speed is VB, and we need acceleration. Now this is very important. Since the motion here, the motion was under gravity, therefore we took G minus 10. But here motion is not under gravity. Particle A is in contact with the table. So you cannot use G here. You need to get acceleration of particle A for this motion. And you need to resolve forces for this. See, for A slack, for this acceleration, you need to use this equation. Tension is greater than friction. So tension minus friction is equal to Ma. Since string becomes slack, therefore tension will be 0. So minus friction is equal to Ma. Therefore A slack must be minus friction upon mass of A. This equation will help you to get the acceleration of this particle from this to this motion, or for this motion. What if the table is smooth? Let's suppose table is smooth, then acceleration must be 0, because friction is 0, therefore acceleration is 0, therefore speed will be constant. Meaning if this speed is 2, therefore this will also be 2. So make sure you read the question carefully. You can have both the situations, and both the situations have already come in the exam. When table is rough, then use this acceleration. When table is smooth, then acceleration must be 0 and the speed is constant. The most important part of this situation is acceleration. You must know how to get the acceleration for slack when the string becomes slack. Next case, case 3. Well, we have inclined plane. This is particle B and this is particle A, and weight of B is greater than weight of A. And when you release the system from rest, then A will move in this direction and B will move in this direction and A will move in this direction. B will move down the slope and A will move up the slope. And you all know how to resolve forces on inclined plane. This is the component of weight which is perpendicular to slope, mg cos theta, and this component is always parallel to slope, and down the slope mg sin theta. This is the tension in this string and this is the normal reaction. Tension, mg sin theta, mg cos theta, and normal reaction. Since B is moving down the slope, therefore you need to use this mg sin theta greater than tension and friction. This is for B. For A, tension is greater than mg sin theta plus friction. So with the help of these two inequalities, you can get two equations and you can solve those equations for tension and acceleration. Given that A does not reach the pulley, so when B strikes the ground, then it strikes the ground with speed VB, and this would be the speed of A at this position, because in one string speed will remain same. So when given that A does not reach the pulley, means A would come to rest before the pulley at somewhere, and does not reach means it will come to rest, therefore its velocity must be 0, final velocity or speed. We are considering speed, so final speed is 0. Initial speed is VB. Now we need acceleration for this motion when this string becomes slack. For that we need to use this inequality. T greater than friction plus mg sine theta, you need to bring both on left side and use mass times acceleration. Since the string becomes slack, so T must be 0. So you can get the acceleration from this equation. So you will use this equation for A slack. What if pulley is smooth? What if the inclined plane or slope is smooth? Then friction must be 0. Therefore, A slack must be this thing. This must be 0. So A slack must be minus g sine theta. The most important part of this case is also A slack. You must know how to get A slack. You must use this inequality for that. And then you need to equate T to 0. Next case, number 4. Now we have one particle on slope and one particle is hung freely in the air. And B is greater than, B is heavier than A. So when you release the system from rest, B hits the ground with the speed VB, and that will be the initial speed of A. You can write this as UA to make it simple. C. Since B is moving vertically downwards, therefore weight of B is greater than tension. And since A is moving up the slope, therefore tension must be greater than mg sine theta plus friction. This is here. When the string becomes slack, then again you need to use this inequality. So tension will be 0, minus friction minus mg sine theta, m is slack. And for a smooth slope, A slack must be minus g sine theta because friction must be 0. In this case, they are saying A reaches the pulley with the speed VB. So we can easily get V with the help of this acceleration or this acceleration. It depends. For a smooth slope, use this acceleration. For rough slope, use this acceleration. Number 5, case 5. Well, this is the initial situation. We have 3 particles, A, B, and C. First, we need to resolve forces very carefully. Since weight of B is greater than weight of A, meaning B is heavier than A, and when you release system from rest, B will move in this direction, A will move in this direction, and C will move in this direction. Number 1, consider the motion of A. Since A is moving in this direction, therefore tension T1. Well, this is one string and this is the other string. So we have 2 strings. So in this string tension is T1, in this string tension is T2. So T1 is greater than weight of A because A is moving vertically upward. For B, the situation is very simple. B is moving vertically downward. Therefore, weight of B greater than T2. For C, make sure you resolve forces very carefully. C is moving in this direction, therefore T2 must be greater than sum of these two, friction and T1. So with the help of these 3 inequalities, you can get 3 equations and you can solve those equations for tension and acceleration. Well, when B hits the ground, it must hit the ground with the speed VB, and this will be the initial speed of this particle, C. And since B hits the ground, therefore, and the speed of C, particle C is not 0, therefore C will move towards the pulley, will continue to move towards the pulley in fact, and let's suppose C does not reach the pulley, therefore we need acceleration of C. This is a final speed of C, 0, initial is VB. Well, for TA, you need to use same inequality because A is moving vertically upward direction. For C, you need to use this inequality. T2 must be 0. T1 minus friction is equal to M slack. With the help of this equation, you can get A slack for the motion of particle C. So you always use these inequalities in the later part. Case 6. This is a very simple case. Uh, we have a force which makes angle theta from horizontal or from table on particle A. Force exerted on A and makes angle theta from the table. So this is the situation. And this system, when you release the system from rest, then A will move in this direction. Therefore, B will move in this direction. So you need to resolve F. There are two components of F, F sine theta, F cos theta. So this component of F is responsible for the motion of A away from the pulley. So F cos theta must be greater than sum of these two. And T is greater than weight of B. And R plus this is equal to W because there is no motion perpendicular to table. This is the way to resolve forces for this situation. Next case. The resultant force Fr exerted on the pulley by this string. This is very important. Exerted on the pulley by this string. So direction should be this. This is the resultant force exerted on the pulley by this string. If this angle is 40 degrees, so this must be 50, and this force is at the center, so both angles must be equal, 25 each. So you need to resolve forces at P over here. You need to resolve Fr separately and these two tensions separately. This is for Fr. So Fr has two components. This is Fr sine 25 and this is Fr cos 25. And these two tensions are here. This angle is 40 degrees because of alternate angles. And we are resolving forces at P, so tensions would act away from P. These are the directions of tensions, this and this. You need to resolve this tension. This is T tension. This tension is here. So this tension has two components. This is T cos 40 degrees and this is T sine 40 degrees. And this tension is acting vertically, so it has no component. Now you just need to either equate vertical components of both or horizontal components of both. You can either equate this to this or this with sum of these two. So you have options. Either equate sigma x of both or sigma y of both to get the value of Fr or T.